Hi grade 12s, welcome to Learn Extra Live Physics, and finally it's your turn. I know that there's a certain amount of you that have been watching since grade 10. You know, we've got Kashifa, who watches almost every show in every subject, and a whole bunch of other you, like Nele. So guys, just give us a shout on the page, let us know if you are watching. So for grade 12s, tonight we're talking about
wave diffraction. Okay, it's quite a difficult one. A lot of people really struggle with the concept, and we're going to be talking a little bit about Huygens, and we're going to see what he says.
Okay, it sounds terrifying but fun at the same time. So guys, we're going to do this together as a team, and don't forget to only post questions that are relating to the topic we are talking about tonight on the page and on Twitter. That's facebook.com/learnextra, or chat to us on Twitter @learnextra. We'll be going through your questions in the last 15 minutes of the show. This show is also brought to you by Liberty, and they rock. So thank you guys for helping us out and being so awesome. While you're watching, shoot off those questions, and we will be getting to you in the last half of the show. Without further ado, we're going to go to a quick break, and we'll be back with you shortly. See you now. Hi guys, and welcome back to Learn Extra Live. This is grade 12, and finally it is your show. I know that you've all been waiting since grade 10, 11, because I know you've all been watching. If I say your name wrong, I'm so sorry. Horalile says, I love physical science. And Dipolelo says, okay, but hopefully Phil's not going to blush too much. She says, or he or she says, I wish Phil was my physics teacher. Very good teacher and clearly understandable. So at least we know that Phil's doing a good job. Kersha, sorry. Oh, shucks, happy moment, here we go, grade 12s. And Sidimo, Tlale, always on the page, always talking. Don't forget, guys, it's facebook.com/learnextra. Chat to me @learnextra on Twitter as well, so it's a quick way to get those questions back and forth. Don't forget that we are giving away a Casio calculator in this show. We'll be announcing the winner on the page tomorrow. And the way that you win this, guys, is that you just comment on the page, you help each other out, you be a mindsetter, and I think that is the best way that you're going to get this calculator, and it's really awesome. Sidimo says, hey, what's up? When are we doing electrochemical reactions? I need a matric physics buddy, please. Any volunteers? So guys, that's exactly what we need on the page. We need you guys helping each other out. I know Kashifa and Anissa and Danele and Mbuso, you all do it fantastically. Guys, help each other out, learn more and learn extra. And now I know I'm taking a lot of Phil's time away. He's going to be very angry. So Phil, I think without further ado, let's take it away and let's learn about the diffraction of light.
Absolutely. Thank you so much for that wonderful intro. What we're going to be dealing with today is we're going to be dealing with the diffraction of light. Now, this is a topic which scares a lot of people, really doesn't need to. And I'm going to be showing off a little bit of my art skills. We're going to try draw together, and we're going to try figure out what the diffraction of light is, how it's asked in an exam-style question. And I'm going to be giving you something like an exam-style question for that challenge question. Most of you are working through these at home, and we're going to be working through that challenge question a little bit later on in the show. Okay, well, let's first figure out what the diffraction of light actually is, how to work with it, what the calculations mean, why it happens. I'm going to be taking you through this step by step. Okay, well, first of all, you probably recognize this diagram. And lucky you, matric, you're one of the few last years where this is still in the syllabus. I believe that there are changes underway. But fantastic that they've actually got this inside. Now, this actually explains why light does very weird things when we push it through a small entrance between two barriers. So what I can see in this diagram is that I've got waves which are approaching. We're going to try to explain what happens once it's actually passed through there. Why do they go from being nice and parallel to being this widened out net of waves? So why do they go parallel and then spread out from that point? Let's figure this out. Well, diffraction is easily recognizable. I actually find out that the shape of the wave changes as it comes out of that slit, and we'll find that this is because of Huygens Principle. Okay, now Huygens Principle is actually something really easy to understand if we take it apart into pieces, and that's what I'm going to do for you today. Okay, but before we do that, what I'm going to be doing is I'm going to be giving you a diffraction challenge. Now, what I've got here is a diagram with a 0.01 millimeter slit over there. There's the opening between the bands. And I'm going to draw a few things onto this, and we're going to try to see if people can actually manage to follow this. This 0.01 millimeter slit over there is the opening inside this, and I find that I've got a central band over here. Those of you that have done this section will know what I'm talking about. If you haven't, don't worry, we're going to teach you. I've got a spreading out of the central band, and this is the first minimum. Sometimes a lot of people are wondering what that is. This is my first of the dark bands. I've got a light band in the middle there, and I've got some dark bands stretching out to the side. So this is my first minimum. Now what I've told you over here, I've told you that there is some information over here. I've told you that there is 700 nanometers as my wavelength, so that's some pretty important information. I've got a long wavelength, nice red wavelength, and I'm going to show you how that affects diffraction. So my red light is shining on here, and I know that my central or my main band is a certain width apart. I know that the screen that it's projected on is 1 meter away. I've got several options over here. I'm just going to read them out because they might not be that visible. I just want to make sure that people at home can actually figure this out. The first option is A, which is 7 times 10 to the minus 5 meters. Okay, that's pretty tiny. The next option is 1.4 times 10 to the minus 4 meters. The next one, 1.4 times 10 to the minus 1 meters. The next one is, sorry, we've had a bit of a mistake there. So that's 7 times 10 to the minus 2. Let's actually make that a D because we've corrected that later on. So that is option D, sorry. If you're choosing option D, that is it. 7 times 10 to the minus 2 meters is that correct answer there. So if we run through these, what I'll actually find is that one of these is correct. I want to know how wide is that central band. Okay, now let me just re-emphasize what's going on there. My central band over there, how wide is it? How far apart are those two minima? That's what I'm asking you. I want to know, is it 7 times 10 to the minus 5, 1.4 times 10 to the minus 4, times 10 to the minus 1, or is it 7 times 10 to the minus 2? There's a couple of options over there. I want you to work towards this. If the screen is 1 meter away, and I've got 700 nanometers shining on here, lots of information. So let's just figure out what that important information is. There's the slit. That's how wide the slit in the barrier is. I know that I've got 700 nanometers of my red coloring, and it's 1 meter away from the screen. A lot of information. Let's try and see if people manage to get working towards that. I want to know how wide is that little piece which I've circled in red. Okay, a lot of information to deal with. Quite a quick calculation. Just make sure that you send in your calculations with your answer. I don't want to see any guessing. If I see guessing, I'm going to ignore your answers completely. I want to see full working out, and so do your examiners at the end of the year. I want to see how you arrive at your correct answer. Okay, well, let's get into the nitty-gritty of this. Let's figure out where this all came from. Okay, this guy who is dressed up in all these weird clothing, okay, this is Christian Huygens. Huygens managed to figure out something really amazing. He managed to figure out that each point along a wavefront, so that means every little piece along a wavefront acts as an individual disturbance. Okay, now that might be a little bit difficult to grapple. Now if you're viciously writing this down at home, that's okay. I'm going to explain. I've made a couple of animated diagrams, and we're going to work through them, and we're going to try to figure out what Huygens Principle actually means. So he said that each point along this wavefront acts as an individual disturbance. Now that might be a little bit weird to conceptualize. Now if you see a little point in the ocean, you're wondering how is this ocean wave made up of many points? That's very, very confusing. I'm going to show you some diagrams to actually help you along the way. So Christian Huygens, really amazing guy. He's managed to figure out how diffraction has occurred. Now diffraction itself is actually quite simple when I apply his principle. Let's get right into it. Okay, well, let's start right at the beginning. I have my waves merrily approaching my barrier. The barrier is going to get in the way. What we'll notice is that at the moment, I've got a ray. Let's actually label this. If you're drawing this, let's get this right. If I've got an arrow showing the direction of waves, remember, all the way from grade 10s, I called this a ray, and hence the word a ray of light. These guys, these yellow guys, let's actually label them in yellow, and let's make sure that we keep track of it. These are my wave fronts. So I hope that you can read that at home. Now, wave fronts are one point along a wave. Now, if you don't know what a wavefront is, it's a point along a wave which is all in phase. So if you decide to choose all the points along the crest as your wavefront, that's absolutely fine. A wavefront is always the same piece of many waves. So I'll find that these lines represent the same piece on multiple waves. If you look at the waves from the top, this is what I'm going to see. I'm going to see the straight lines, and I call those wavefronts. I don't want you to worry too much about the terms and the definitions yet. we're going to get there, it's going to become more important. Now here's where things become a little bit tricky. I think that because some of it goes past, I anticipate that my waves are going to stay nice and parallel, and we're going to find that we've got all these waves on this. That doesn't actually happen. Something very strange happens when waves go past a barrier. And what I've done is I've tried to animate this in little sequences, and we're going to try to see what goes on when I move to my next diagram. There it is. Now this is where Huygens Principle comes into play. I've chosen to take one wavefront, and I've chosen a couple of points over here. Okay. Now, I'm saying that the wave is moving past the barrier. At the moment, it's still in line with the barrier. There's no problem at all. I've still got a nice straight wave. Okay. But now what I'm going to do is I'm going to look at the wavefront as a line of disturbances. Now, these points which I've shown you, picture them to be like stones which I drop in the water. Now, each point along the wavefront, or each point along that wave, is going to act like a new disturbance. They're going to create new waves. So what we're going to find is that these points over there, I'm going to find that each one of those points is going to act like a source of new waves which are going to move out. So if you had yourself and 3 friends and you were standing in a line, you represent the wave. Now what I want you to do is picture yourself all dropping the stone at the same time. So I've got these 4 stones which are now dropping into that water. This is what Huygens Principle actually means. It means that I can take a wave and I can chop it up into little pieces, and each piece is to act as a new disturbance. Now, if you can picture 4 things which are being dropped into the water at the same time, something very interesting is going to happen. So, as it moves past the wave, let's try to see if we can get this to come up. I noticed that these 4 points actually make new waves. So I'm going to do that again. So they're going to create new waves which are going to move outwards from that point. And there it is. If I've got these disturbances, let's actually draw in a couple of arrows to show that they're actually shooting out these waves in all directions. So each one of these disturbances is trying to send out their new waves. So all of them are trying to send out their new waves. So all of these stones would be sending out these waves. And as they move, let's actually move that back in line with there. As they move back in line there, what we're going to find is that they're going to create their new little waves. I call these secondary wavelets. Now, you might want to make notes on this as we go there. So secondary wavelets. Okay, and secondary wavelets are the waves which come from those points of disturbance. So those waves are going to head out from that central point. Okay. Well, secondary wavelets are all fine and good, but this is not what I see on the other side. So Huygens Principle, well, does it really help us yet? We're not entirely sure. Well, let's see. Now, if we were to take these out, let's take them away, and let's try and study this picture on its own. I'm trying to see what happens to secondary waves once they come out of the side here. I'm sure that you'll notice is that you actually start to create a new line. If I move those left and right, we can actually create a line of there. So I'm just going to leave them back in their original position, but what you'll notice is that there is actually a new line which is made on the front of those waves. Okay, well, what does that have to do with us? Let's see. Now, if I've got a line to draw on these, I'm going to call this a secondary wavefront. This is a new wavefront which is created by those many little secondary wavelets. Now, once again, I'm going to draw in the secondary wavelets the way that they made the new wave. This is actually the shape of the new wave. I don't have these round waves anymore. I don't have them anymore. All that I will see is one smooth wavefront. I won't see secondary wavelets anymore, but I want to show you where they came from. Now, Huygens Principle is quite a difficult thing to understand. Let's try and explain some of the points in line with this. Let's actually try to put down some of the main points. Each point is making secondary wavelets. So that's my first step in explaining Huygens Principle, is that each point makes a new wavelet. So there we go. Each point makes a new wavelet. So it makes a wavelet. These wavelets become the secondary wavefront. So I'm going to find that each one is going to create its own waves. Those are going to move out, and I'm going to create a secondary wavefront. Now, if I take out those little wavelets, all I'm left with is a wave which is now curved itself. And that's quite a difficult thing to understand without using Huygens Principle. Now comes the tricky part. What happens if I introduce secondary barriers, or if I've got other barriers? Now, I'm sure that you can see at home, I've got two barriers. What happens when 2 points are actually approaching from the left-hand side? So if I've got two waves which are coming through here, what's going to happen? What happens when I've got points over there and I've got points over there? How are they going to make their new wavelets, and what will be the pattern on the other side? Well, let's bring up the first one. So I've got the first wavelet which is being created. So this is creating its own disturbances. So this was the initial point. I find that I've got the one set of wavelets which are being made, and I'm going to try and see what happens when I've got a new set of wavelets which are coming over there. Now, I've made them in two colors. Now, this is quite a lot to look at. So I'm going to do it without, so let me just do that again. I'm going to show you that secondary bit coming in. Now, I don't want you to sit at home and try to draw this. This is going to take quite a while. This is inside textbooks. It's inside our workbook. This diagram is really difficult to draw, and you won't have to do it. However, I do need you to explain it. So let's try use Huygens Principle. Huygens Principle says that I've got these 2 points which are coming in. So I've got my 1 point, and I've got another point which come in through the slit, and they create secondary wavelets. One in white, one in yellow there. So I've got one in white, one in yellow. What I've done is I've shown what happens when these secondary wavelets come out. If I draw a nice semicircle around that, I can actually see that I've got this curved line moving all the way around this wave. And I can actually see why I get a curved wave on the other side of the slit. So that's the first thing. So these secondary waves make a curved secondary wavelet. So that's the one thing, is that the wavelets make a curved. Now that's the most immediate thing. They make a curved wavefront. Now that's not all that happens though. Now the secondary wavefront, I'm sure that you'll notice that there's something familiar happening inside here. I've actually got waves which are crossing over each other. And if you remember from grade 10, something is going to happen at each one of these points. Every time one of these wavefronts, because remember that they are in phase. In phase means that they can interfere. I'm going to draw some lines on here. Every time I see two wavefronts crossing over each other, I'm going to find a point of interference. There's one, there's one, there's one, and you'll actually notice that there's a very amazing pattern forming here. I can draw another set of green lines. Watch me do this. Watch me do it carefully. Every time yellow crosses white, I'm going to draw a point. And that means that I've got interference taking place. So there we go. I've got there, and I've got there, there, and there. I hope that you can see that there's a nice straight line happening over there. And I can see that I've got a straight line of interference happening over there. Once again, there's another line up at the top. And I can actually figure out that there is a pattern going on here. Something very strange is happening down the middle, down the top, and down at the bottom. And we can actually find that interference is taking place here. This is how we create a diffraction pattern. These lines themselves are going to be lines of interference. Now, because they're in phase, now that's quite important to note, is that wavefronts generally are all in phase. And that means, and this little 3 dots means, therefore, in phase, therefore, I've got interference. Sorry, that's very, very unneat, and let's just make sure because people are writing notes at home. So I've got interference. Okay, interference is very, very important. Okay, so I've got interference. Fantastic. Okay, so they are in phase, and there is interference going on over there, and I want you to realize that this interference is constructive. Okay, now this may seem like a little bit of a mess, so what I'm going to do is I'm going to clean this all up, and we're going to figure out what to do with all of that. So here what I've done is I've actually put these secondary wavelets. We're going to try and see what an interference pattern actually does. Okay, just remember that my secondary wavelets have come through the slit. They're busy splitting up. what I've done is I've put a screen. This screen is to display what's happening with the light. Is it going to be light? Is it going to be dark? And let's actually work with the secondary wavelets. Let's see what happens. Okay, well, in between there, let's try to see if we can't bring them up. There we go. I've got my 3 lines, which I brought up earlier, my 3 lines of constructive interference. So what you'll notice is that all of these were where a white line joined with a yellow line. White line, yellow line means that there's 2 wavefronts interfering with each other constructively, and I've just drawn 3 straight lines there. The reason that I've done that is because I want to show you what the result is of intensity on the screen. Now, if I take a look on the screen, what I'll notice is that there's actually a place where I find maximum brightness. Now, you're going to notice a diagram very much like this, and this is the same diagram that I find inside my challenge question. Every time there's constructive interference, I get a very bright image. Now what that means is that I've got a maximum. This is actually a graph of intensity. The places where that peak is the biggest is where I've got maximum brightness. I've got lots of brightness. Now, the other thing which a lot of people don't realize is that there's places where there's no brightness. In other words, those are called dark bands. Now, dark bands are caused by destructive interference. Okay, now destructive interference is where obviously they're cancelling out. That's grade 10 work. Destructive interference is when 2 waves are actually making sure that there is nothing. So I can see that there is no wave over there. There's lots of wave down the middle. Now, when I asked you earlier, what is the width of the central band, what I was talking about, and this is the first clue to our challenge question, there it is. I'm trying to figure out how wide is that central band? How wide is my minimum to minimum distance going to be inside that question? I hope that people are getting that. I'm not sure how we're doing for time, but I think we're doing on pace. And
yeah. How are you? Do you need some water? Would you like to take a breath?
Well, I'm really enjoying this work, but I think we need to give the learners a little bit of a break.
What we're going to do is we're going to give you guys a break, and then at least that way I can pull over and have him look at all the questions that you're asking on the page. So do that, www.facebook.com/learnextra. Also chat to me on Twitter @LearnExtra, and we'll help you out with anything you're struggling with. Let's take a quick break, and we'll be back with you shortly. See you now. Hi guys, and welcome back to Learn Extra Live. This is grade 12 physics with Phil in Indiana, and I hope that you're all tuning in and you've been cracking along with that challenge question, and the answers are coming up fast and furiously. You will see that we have posted on the page, so you can get it there, download it to your phone. I think that's always awesome. You know, maybe even download it to your phone, and then you know the answers, and you can go and test your fellow learners that aren't watching Mindset Learn, and then show them how smart you really, really are. So Phil, let's take it away.
Thank you very much, Indiana. Okay, well, a couple of people are wondering about how to actually start approaching this challenge question. Well, the diffraction equation is obviously the first port of call, and I want to explain the bits and pieces because there are a lot of bits and pieces which people are a little bit scared of. So what I'm hoping to do is actually dissect this equation and try and figure out what's going on here. So this particular equation, I've got it here. What I'm going to be doing is I'm going to be labeling the bits and pieces. I want you to do that as well because it's part of the learning process. I've got to figure out how to work with sine theta is equal to m lambda over a. Okay, so I've put it up there nice and big, and we're going to run around and we're going to try and figure out how to label this thing. Okay, so let's get to it. Let's try and figure out what these are. Some of you are already asking questions. I'm going to ask you to be a little bit patient with us. We've got a time for questions right at the end of the show after we've answered our challenge question. I hope that you're hard at work on that, and I'm sure that Indy's hard at work on the page, but let's get to this.
There's so many grade 12s here.
Absolutely. Absolutely. Well, I'm glad that people are taking an interest.
Exactly.
I would assume that they've got an interest. They're writing a very big exam in a couple of months' time, and I hope that they're working hard on it.
Not to make them panic or anything, hey,
Not to panic, but they should panic. Okay.
Don't panic.
Okay, all right. No, well, we're here to help you. And one of the things that you can do is if you've missed shows or whatever, you can actually go take a look on YouTube, can't they?
Yes, I'll post that link as well.
Absolutely.
Good idea.
Fantastic. So if you've missed the show, if you're worried that you didn't get all the notes on, we are fantastic with that. We post everything online, and hopefully we're going to help you with that. Okay, well, let's carry on with the construction of the lesson. Let's see what sine theta actually means. Now, a lot of you are wondering how you landed yourself inside a maths lesson. Okay, but sine theta was something which needs to be put in there. Physics and maths are intertwined, they are related. So sine theta is starting to talk about the angle of diffraction. Now I'm going to talk to you a little bit about that. This is the angle of diffraction. So it's the angle of how wide is that thing actually going to spread out. So the angle of diffraction, there it is. Okay, but the question is, the angle of diffraction, what does it depend on? Now, there's three variables. Only one of them you're actually familiar with. Now, that should be this guy. We should know exactly what he is. That is my wavelength. Okay, now be very careful about your wavelength, because your wavelength has got to be in meters. So my wavelength in meters is something that I've known since grade 10. My wavelength is dependent on the question, and the challenge question was 700 nanometers. There's a problem there because I gave it to you in nanometers. Another hint. I've got meters over here. There's my wavelength. Let's figure out what M and A actually mean. This is not mass. This is not acceleration. Please, please, M over A is not mass and acceleration. A lot of people are getting this confused. Okay, so M in this case. Now this is the number of the dark band. Now that's not going to make a lot of sense until I show you something. But let's just take it as the number of the dark band. Now, when I take a look at diffraction, I'm going to create those light bands, I'm going to create those dark bands, we're going to go back and we're going to try to figure out what this M actually means. Now, M is always an integer. That means that it's always going to be a whole number. It can only be 1, 2, 3. It's always going to be that. No fractions, please. Okay? This is always going to be an integer. If you don't remember what that means, this number is usually 1 if you're not told to go to the second or the third or the fourth dark band. A is the last piece. This is the last piece of the puzzle. I know that A is the slit width. How wide is the slit between the two barriers when I close it up together? How wide is that gap in between them? So there's my slit width. And once again, I've got meters because this is a distance. I've got a wavelength in meters, I've got a slit width in meters, and this is going to give me an angle of deflection, or diffraction rather. And I know that this depends on which number dark band I'm actually looking for, because it's going to get wider as that number gets larger. Okay, now a quick thing. I've got to remember that theta is part of sine. So sine theta is one thing. It's sine of an angle. It's an operation. Now, if you don't know what that means, it means it's an instruction on an angle, which gives me a number. So sine theta is just a number. If you don't understand any of that, that's absolutely fine. I just need to know that theta is not the same as sine theta. And I can't think of them as separate things. I can't move sine on its own because it's part of this. That's what I'm trying to get at. A lot of people think of them as separate objects. So let's go through this again. I've got my angle of diffraction, which I apply sine to, the number of dark bands, okay, which one I'm looking at, and then the wavelength and the slit width, both in meters. So I hope everyone's ready to work with this, and I'm going to give a little bit of advice on how to actually implement this. I hope that's going well. Okay, all right, let's jump right into it. This is a horrible question. I managed to find this inside a past paper of yours. This is a standard matric final question. So some of you at home are saying, well, how do we actually get this done? And I've actually taken this straight out of a final. I think this was the 2010 November paper. Okay, so let's work through this. Let's try to find out the information that I need to do. And let's try and figure out if I can't figure my way through to the answer. So let's just get that out of the way. And if you're frantically copying this down, don't worry. My director's got it up on the screen there. And what I'm hoping that you can do is calculate your way through this. So there's a lot of information here. So I'm going to read you through it, and we're going to try highlight or underline all the important pieces of information. I've got light of a single frequency. That's quite important. Light of a single frequency passes through a slit. Okay, that means that we're dealing with diffraction. So that's all the information that I can get out of there. The first minimum. Now, this is a really weird word. I usually talk about a minimum in maths when I'm talking about the bottom of a graph, and this is the same. The first minimum, they're actually talking about a dark line. Now, that's something which absolutely floored the learners. When I discussed this question with them, they were saying, oh, minimum, maximum, what are they talking about? They're actually saying, which dark line? Okay, so it says the first minimum is observed at point P on a screen. Point O is the midpoint of the bright band. Now this is very, very weird. Bright bands and dark bands and all of that. OP is 2.5 centimeters and the slit is 3.2 times 10 to the minus 5 meters. Okay, so lots of information. Let's try and figure this all out. Okay, so I'm going to go through this in little bits and pieces. I think we're going to take a break in between and give you a chance to actually work this out, come back, do the challenge, answer some of your questions, and let's work through this. Okay, so I've got O is the midpoint of the bright band. Now, what I'm going to do to help you to try to figure out what minimum and maximum actually mean is I'm actually going to draw in the maximum. Now, this is something which you might want to do. I've got a maximum, and it tells me that P is the first minimum. Now, the red might not look so good on the black, so what I'm going to do is I'm going to point this out in yellow. That is my minimum. That is the place where I'm going to identify a dark band. Tons of info. I'm told that OP is 2.5 centimeters and the slit is 3.2 times 10 to the minus 5 meters. Okay, now what I've got to do is I've got to figure out what's going on here. Now, what wavelength of light are we working with? OP is 2.5 centimeters, and I've got a slit of this, and I'm a little bit confused as to where this is going. So what I'm going to do is, I think it's time for an ad break, and we're going to let the learners work their way through this, try and identify the important information, see what they do have and see what they're still looking for, and come back and hopefully answer our way through this.
Exactly. Okay, guys, we're going to take a short break. Phil's going to come and have a look at the page and see what you guys have to say. Without further ado, we're going to go to a quick break. So the faster we go to the break, the faster we get back. See you now. Hi guys, and welcome back to Grade 12 Physical Science Learn Extra Live. I know that you guys hate breaks, but sometimes we've just got to give the teachers a bit of a rest, hey? I'm telling you. So guys, I just wanted to let you know, please keep chatting to us on Facebook and on Twitter. We are answering your questions in the last 5-10 minutes of the show, so it's very important that you let me know now what you are struggling with, and it has to do with what Phil is talking about specifically. Please, please, please. Challenge question is coming up, the answer. Let's see who gets that right. And before we start, I want to give a big up to Liberty for making the show possible. You guys rock. And without further ado, Phil, I think this is the home stretch.
Absolutely. Thank you, Indy. Okay, well, a lot of you have managed to figure out that there is some missing information. So before the break, I described to you a question where we had this minimum and minimum spacing. I need to tell you that if the wavelength is 600 nanometers, calculate the distance between Q and the slit. So what I'm going to do is, with this piece of information up on the board, let's actually move that out of the way. I think I'm making a little bit of a mess on our nice writing here. There we go. What I'm going to be doing is we're going to take a look at how to solve this all out. I'm going to redraw my question, and let's try and figure out what is actually meant by most of this. So let's work in yellow so you can tell the difference between our question and our answers there. The wavelength is 600 nanometers. Now, calculate the distance between Q and the slit. Let me just remind you what that actually all means. Let's go back to that diagram. There's my Q over there. I want to know how big is Q. So Q is how far away that screen is from there. Now, a bit of a problem. My equation doesn't actually tell me anything about that distance. It doesn't tell me about the distance between the screen and that slit. So what I've got to do is I've got to use information that I've got. I know that I've got a bright band. OP is 2.5 centimeters. Fantastic. I know that the slit is 3.2 times 10 to the minus 5 meters. Okay, I've got some information that I can work with. Let's try and figure out what Q is. I'm going to show you how to use it on the calculator. We're going to try work with that, and we're going to try see what goes on there. So I'm going to work with this. I know that I've got 600 nanometers as my wavelength. Let's try see what we get. Let's substitute. Let's see what we get. I've got 600 nanometers as an answer there for my wavelength. Some of you were asking for what is the wavelength. Let's see how we can use our information. Okay, I know that OP is 2.5 centimeters. That's quite useful. I know that if I draw a triangle there, I know that the width over here is 2.5 centimeters. That's quite handy to know. I know that Q is the other part of that triangle. Now, the only way that I can work with all of this is if I actually start working with an angle. And the cool thing about this is the only way that I can work out that angle is to use my original equation. Sine theta is equal to m lambda over a. I've got lambda, there it is. I've got a, I've got it, and there it is. There we go. I've got 3.2 times 10 to the minus 5 meters. Fantastic. All right, now do I have m? Now some of you are asking, the first minimum. The first minimum actually gives me m. The first dark band, that means that m has got a value of 1. Now, what I'm going to do is I'm going to set this all up, and I'm actually going to leave you with a little bit of time to try and figure this out. And while I'm leaving you with that time, I'm going to work you through what's going on with this triangle. Okay, so now if I've got sine theta, and that's equal to m lambda, let's try to see what I've got, and let's see what I don't. Do I have sine theta? Well, first of all, I've got to put it into my calculator. I'm going to show you how in a minute. What about m? M has got a value of 1. That is my first, and first means 1 dark band. Lambda, I've definitely got lambda, that is 600 nanometers. A, I've definitely got, and that's my slit width. I can actually work with this. I can get sine theta from all of this very, very easy. That means that I can get my angle inside my triangle. This is a huge clue for the challenge question, and I'm sure that Indy's busy talking way through the page, and there's a lot going on there. Let me substitute my numbers, and then we're going to go over to Indy to find out what the people are thinking, and we're going to get back to this question. Okay, so let's substitute. Let's find out what we've got. So I've got sine of theta, and that's equal to, remember, m is the number of the dark band. Somebody asked on the page, what happens if it's a second dark band? Doesn't matter. That means that m just becomes 2. But in this case, I've only got 1. There it is. So there's 1. What about my wavelength? Okay, so my wavelength is 600 nanometers. Nano means times 10 to the negative 9. Okay, you should know these multipliers very, very well. The only thing left to put inside this equation is a. So a is 3.2 times 10 to the minus 5. And there it is, 3.2 times 10 to the minus 5, and that's all meters. So let's just check that we've got everything. I've got my m value, which is the number of the dark band. I've got my wavelength. I've got my slit width. All that's left to do is to punch this into my calculator. What I'm going to do is I'm going to ask Indy to see if there's any questions on the page to do with this, because I actually want people to go forward and calculate this. What I'm going to do is I'm going to go fetch our on-screen calculator. Just need a moment or two to do that. What's happening on the page, Indy?
Okay, let's have a look. Guys, I have put up the link to the YouTube, so you guys can get all of the lessons and download them there. However, you're going to have to wait about a week or so for this lesson to be uploaded onto YouTube. And that was a question from Mpho. We do have from Colin. He says, how does wavelength and the width of the slit affect diffraction?
Very nice question. Okay, all right. Well, we've got our calculator. We've got a selection of calculators, but we're going to get to that question.
Okay.
How does slit width affect the diffraction? Okay,
Yeah,
well,
yeah.
I'm going to deal with that. But before we do that, let's just finish this off, and then we'll go through
Okay.
those questions.
Okay, awesome.
Okay, here we go. Okay, so we've got our calculation over here. Let's see how we put it all inside. Let's figure this out together. Now, I want to show you some of the problems that people are actually finding when they're using some of these calculators. They're saying, fantastic, the calculator can solve all of my problems. Watch the buttons that I press. Your calculator might be slightly different to this, but I want to make you aware of some of the fantastic features of one of these calculators that we're actually giving away. So there we go. I'm going to set up my fraction. So I'm going to say 1 inside brackets just to make sure that we multiply. That's not the part that I'm worried about. Here comes the piece that really, really, really makes me very angry when I'm marking people's papers. They don't know how to actually punch in nanometers into their calculators. Now, if this is you, that means that you've got a bit of work to do. So 600, that's not the part that I'm worried about. Here comes the problem. They see times and they reach for that button. They reach for times. That's not the button that I want. Watch the button that I push very, very carefully. I'm going to push the bottom one, the one which says times 10 to the x. That's right in the bottom, in the middle. If I push that button, that tells me that I've got times 10, and whatever number comes next is going to be my exponent. So I'm going to put in negative 9, and there's my button to change to negative over there. So negative 9, and close my brackets. So I want to make sure that everyone's got exactly the same thing. I've got 600 times 10 raised to the power of negative 9 to show that I've got nanometers. Down to the bottom, same thing. 3.2, practice this as we go. 3.2, I push that button again, -5. There it is. So -5, and I've got everything going on there. Fantastic. I get an answer. The problem is, this is not an angle. That is not an angle, and it's not the angle that I'm looking for. This is sine theta. I'm going to find that sine theta is equal to 0.01857. That's not what I want. What I want is the angle. Now, how do I go from sine theta is equal to this number? So 1875, 0.01875. Let's actually write it down. So I've got sine theta is equal to 0.01875. That's really quite a useless number unless I change it back into an angle. Now, most of you at home are already shouting at your TVs. Okay, the way that I change this back into an angle, don't round it off, please. It needs to stay as it is. It's not my final answer. Let's go back to an angle. Okay, I push shift, sine, and here's a very nifty trick. Casio calculators, amazing. So I'm going to say shift sine. Now, this is a really cool thing. It remembers my last answer, and if I push this button answer, most calculators have got something like this. I just particularly like this one. So if I say sine, shift sine rather, of my last answer, there we go, an angle will come out. I've got 1,07. There it is. That is an angle. I know, therefore, that theta is equal to 1,07 degrees. We're not done yet. Okay. All I know now is that I've got the pieces of my triangle. I've got my triangle now with Q as its long side, as the adjacent side. I now know that I've got an angle here of 1,07 degrees. Now, the only way that I could get there is by figuring out all this other stuff. Now, onto a little bit of maths. Let's try and figure out if I can't find a ratio between here and here. Now, if you remember, this is the two parts of a right angle triangle. Really cool thing is, if you're strong in maths, a little bit of trick can get us all the way there. I've got an angle which makes Q my adjacent. This is my opposite. So opposite and adjacent are related by the operator tan. So we're almost there. So I know that tan of my angle of 1,07 degrees is equal to my opposite, which is 2.5 centimeters. Now, we don't have to work in meters here, over my adjacent, which is Q. Okay, well, how do I rearrange this? Well, Q's got to jump over to the left, and I've got to leave 2.5 on the top, and I've got tan of my last answer. There we go, 1.07 degrees. Let's put it into our calculator and see if we get something meaningful. It's going to be quite a large number, because to get something to shift 2.5 centimeters with that small angle is going to be quite tough. Okay, so let's just clear this. All right, I know that I've got 2.5. Let's bring up our fraction. There it is, 2.5 over tan of my 1,07 degrees. It's going to be a fair distance away. What I'm actually going to find is that it's 133.85 centimeters away. That's a fair distance away. So there we go. And I notice that Q is going to be 133. Let's bring up that calculator. I can't remember all of that. 0.85. There we go. So 0.85. Remember that we're still working in centimeters here. Now, if they do ask in meters, that's where we've got to leave it. Very long question. All I could do was work with what I was given and figure it out that way. Sure. That was exhausting. I hope that people managed to follow all of that. I still want to get to the challenge question.
I hope so. Yeah. I think that's what we should get straight to.
Absolutely.
Yeah.
Have people started answering?
Yes, they have. We've got lots and lots of answers. So
Okay.
I think
What I'm going to do is I'm going to put people out of their misery. We're going to go back to that challenge question. Let's go right back to that. And let's try and figure out what people were trying to think about or what they were doing. Let's see what we had here. Okay. Well, a lot of you started to take a look at pieces of information. I'm going to show you some of the things that people are doing wrong. I intentionally gave answers which were misleading. Okay, it's very nasty of me, but what I wanted to do was to make sure that matrics are practicing these problems. Okay, now the emphasis over here in this diagram is something about the units. Now, physics is full of units. If you can't work with your units, you are going to be stuck. So the first one that people really struggled with was that 0.01 millimeter slit was the first problem. We found that inside that slit, I've got a certain number of meters, so I've got to be able to convert that into meters first. and that was my A value. Okay, we're getting there. So what I've got to do is, now because it's millimeters, now there's a few ways that I can actually do this. There we go. Easiest way is actually to use milli. Milli means times 10 to the 3. So there is my slit. Okay, what else? I know that I've got 700 nanometers. There it is, 700 times 10 to the minus 9, and that was my wavelength. Big problem that people also didn't do. The next trick, this one was really nasty, and I hope people don't hate me forever for it. This one was
Let us know on Facebook if you do.
No, I'd never hate my matrix. Okay. Look, guys, I wouldn't have a job without you, and I love teaching you guys. I promise I do not hate you. Okay? It's okay if you're angry at me for setting such a horrible question.
But you're only trying to help.
I am only trying to help, and it's because we love you guys. Okay. Now, the other problem was that this was actually a distance, but it was a double distance. I'm going to draw this out nicely, bigly, and we're going to show you what I mean by that double distance. If you take a look at that triangle, we usually draw a triangle like this to the first minimum like that. Now, here's the other problem. I've actually asked you, how wide is the entire maximum? Now, I have seen this in a final paper, so it is fair game. They can do this to you. Just be very careful. That's your angle, and what you'll find is that there's that distance, and this is usually the one that you calculate, but I want the entire distance. So if you manage to find the correct answer, there it is. The correct answer is C. C is the answer to this challenge question. If you manage to get there, amazing. It means that you've been working very, very hard.
I'm going to have to go and have a look because, to be honest, I thought it was D, and I think most of the mindsetters thought it was D as well. Okay. So you bamboozled us there.
Okay.
So guys, let us know if there is anything you are struggling with, or if there's anything you don't understand. But I think Phil gave us a bit of a tricky one. You asked for a hard one, and that's exactly what you got. Okay. So there you go.
All right,
we have some questions.
I think there is time for a little bit of questions. Somebody asked specifically about the equation, correct?
Yes, yes.
Okay.
Yeah.
All right, now that equation, that very, very tricky one, was talking about the second minimum or the third minimum. Let me just put up that equation, and let's try see if we can't figure out what they were talking about. They asked what happens if I'm talking about the second bright band or the third bright band or even the dark bands. It doesn't really matter. Anytime they start mentioning the second, third, fourth, fifth, they're actually giving you the number for this particular one. What they're actually trying to do is they're trying to tell you the number. Whichever dark band they're talking about or the end of the light band is M. So if I've got 2 or 3, it can be 1, 2, any number of the dark band. So if it's a second, obviously, then it would be number 2. If it's a third, 3, so on and so forth. It's not actually that tricky. What they're going to try to do in your exam is they're going to show you all these dark bands, and it's going to be all this information. It's not necessary. If I've got that dark band number, there it is.
Okay, fantastic. Now let's squeeze in this little question. A few people are a bit confused. But let me take Yvonne's question first. She says the distance between the OP was in centimeters. Why did Phil give the answer in meters?
Okay.
And there's been a few of those, so maybe we can answer everyone.
Okay.
Yeah.
Well, what I've done over there is you've got to work in meters over there. The reason that I've given the answer in meters is because, well, actually, there is no real reason for that. Over here, the central band can be given in centimeters or meters. If you want to work with meters over there, that's entirely fine. But what I'm showing you here is that I've given this slit width in millimeters, got to work in meters there. That's no option. However, the distance between the slit and this has got to be inside some sort of meters. Now, you can work in centimeters, you can work in millimeters, whatever might be the case, because you're going to start using some trigonometry there. My answer over here is also given in meters. It's just to stay with the same unit the whole way through. And that's the simple answer.
Fantastic. Okay. We've got 1 minute left, and I had this question right here, and now I can't even find it.
Perhaps I can answer it online a little bit later. What do you think?
Yes, I think that's a very, very good idea. So guys, that's exactly what we're going to do. I'm so sorry we run out of time, but you know exactly what we say is if we can't get to your questions, please help each other out on the page. I do know that Tuso actually answered Mpho's question. So Mpho, please go and have a look at Tuso's answer, and he has been helping you out there on the page. So guys, thank you so much for joining. Grade 12s. Thank you for a fantastic Learn Extra Live, and we'll see you same time, same place next week. Bye.